everyone. I'm Susan Nash, AAPG. Thrilled to be here today with our very first Lunch and Learn with our Deep Learning Technical Interest Group. And the topic today is Machine Learning, New Discoveries in Reservoir Optimization. Deborah Sacrey of Auburn Energy is here, and she has a more specific title for the paper, but it's really exciting and new discoveries and new possibilities. So I'd like to turn the floor over to Patrick Ng, who will tell us a little bit about the technical interest group and introduce our speaker.
Thank you, Susan. Welcome everyone to this lunch or supper, depending on where you are. And a deep learning group in AAPG is really a technical interest group. I'll give you the link. You can contribute and keep the conversation going after this. Over the last 12 months, at least, we've seen an emerging pattern of using ensemble technique like random forest or clustering technique like support vector machine in automating lithology identification. And also on the seismic side, we have seen the use of deep convolution neural network for map interpretation. Now, what the challenge remains is when we work across the scales, mixing seismic and the Weld laws, the order of magnitude difference in resolution. So today, we're for a treat. Our next speaker, Deborah Sacrey, is experienced geologist and geophysicist. You can think of both the left and the right brain. In addition, she had hands-on experience working software as well as actual field project experience. So therefore today, she can dish up tasty artificial neurons and show us how we can use it perhaps to uncover overlooked or new opportunities. So without further ado, I'll turn control to Deborah.
Welcome, Deborah. And just quickly, everyone, put your questions in the chat box and we'll answer them at the end. Welcome, Deborah.
Thank you, Susan. I'm sharing my screen now. Can you see it okay?
Yes.
Okay. And I probably will go dark on my camera, just so I won't be a distraction to myself. Good day, everyone. I would say morning and afternoon and evening because we've got people from all over the place. But what I'd like to discuss today is some work that I've done, case histories I've done on two different reservoir types, both unconventional and conventional, and show how machine learning can help define sweet spots, help you calculate reserves, and a lot of other technical things that are a lot of fun. I'm going to start out with, let me get this going. Okay. I'm using some software called Paradise. Now, Paradise is a company that was started by Tom Smith, Dr. Tom Smith, back in 2008, after he sold Kingdom, and he was still not ready to retire. So he started playing around with neural networks along with Terry Turner, and the application of learning classification of neural networks using self-organized maps in multiple seismic attributes. And so what we're doing is we're looking at multiple seismic attributes at one time, and we're looking at the variations in those attributes because they all contain information. The premise behind Paradise is instead of a wavelet processing or classification, say like Stratomagic used to do, we're looking at everything on a sample basis, so sample statistics. And so if you have a wavelet that's 20 or 30 milliseconds, and you have 1 millisecond sample rate, then you're parsing that data and looking at it statistically 20 or 30 times what you probably would do when you're looking at a wavelet and mapping zero crossings or peaks or troughs. So this generates a lot of information, but it also lets you see a lot of fine detail in the subsurface. And one reason why we use multiple attributes, like I showed earlier, is that along each sample, each different attribute, the wavelet of that attribute carries a little bit different information in it. And we put all this stuff in a cloud and then have the neurons look for the natural clusters of data in that cloud. And what happens, because each of the data points have an X, Y, and Z to them, when it comes out of the cloud as a cluster, it puts itself back in a volume, very easy to interpret. So what you end up seeing is you end up seeing voxels, and I call them chiclets because they remind me of the candy gum that we used to eat. And the voxel is going to be based on the sample interval that you're using and the bin size of the data. Now, 99% of my work is in 3D, but this process also works in 2D data if you're in remote areas where you don't have a lot of 3D information. Now, in conventional work, in the wavelet, we have what we call a tuning thickness, and that's based on frequency and depth and the quality of your seismic. In the sample world, when we're doing classification of samples, we really don't have that. Since we're looking at sample rate, we're looking at the vertical resolution of the sample statistics is based on the interval velocity of the rock itself from which the sample is taken. So there's no interpolation. And it's based on what it's seeing, regardless of depth, regardless of frequency. So I've been able to find 7-foot thick sands at 11,000 feet in the Gulf Coast. I've been able to see 18-foot porosity intervals in carbonates at 2,100 feet. So it's based on the velocity of the rock at the sample. Now with that, I'll get on to my, I'll get off my soapbox about Paradise and get on to the work I've been doing. This work was actually done several years ago. TGS approached us to kind of a proof of concept and wanted to see how well this classification process would work in an unconventional reservoir in Oklahoma. Most specifically, we're looking at the Merrimack Formation in central Oklahoma across Blaine and across Blaine County and Kingfisher County. So they gave us 195 square miles of data, and the project objectives were to see if we could discriminate production in the formation and tell why some wells were better than others, and understand the accuracy in the neural classification results. Okay, so part of the assumptions and challenges to this was the production is not always related to only geological changes, and because there was a combination of long laterals and straight holes, we decided we were only going to look at the straight hole data because of the variance that could happen between fracking and lateral length and things like that, and to some degree the operators. So the only thing that's static and good in here is going to be what happened with the straight hole data. And that porosity and permeability could not be calculated from the log curves provided in order to calibrate the wells. Because we were using straight holes, most of the wells were drilled in the 80s and 90s. My newest well in there was a 2003, I think. So the log curves were left a lot to be desired. There was difficulty in isolating specific production on the wells through the perforated zone because of the age of the wells and because of the nature of the rock itself. And some wells were shut in at times and not. So they were hoping that we could find being able to isolate specific production and in perforated zones. And again, the decision was made to use only straight holes because of variables in completions in the lateral wells. So the first thing they did was, and this is 195 square miles. You can see the live trace outline right here. And I know that the other writing is a little bit small, but they gave me 35 wells, and they held 5 wells back as blind wells to see how well I could predict what was going on. So what I've done is I've taken the cumulative information for production, and the really poor wells are in green. The medium class wells, and those are wells that have produced 50,000 barrels or greater, are in pink. And then the very best well out of the 35 wells had cummed 240,000 barrels of oil and 2.23 BCF of gas. So this was my star child that I really wanted to look at and see if I could see what was going on in this well as opposed to all the other wells in this 195 square miles. So the first thing I did is I mapped the actual top of the Merrimack Formation, which is Mississippian in age. And again, this is in central Oklahoma in Blaine and Kingfisher counties. And this is the structure map. Now, what you have is you're getting deeper as you go to the southwest because you're going into the fringes of the Anadarko Basin, which is a very deep basin. My good well is right here, the Efficacy well. I have a north-south cross section that I'll be focusing upon, and then I also built an east-west cross section through the medium wells and poor wells. So the data quality is excellent. TGS did a wonderful job, and I have to thank them again for allowing me to do this work. But what I want to show here is the top of the, this is Pennsylvania Big Lime, which in some areas they call the Osage. The Mississippian starts right about in here in this middle section. The top of the Merrimack is this hot pink horizon right here. And then you get into the base of the Woodford, which is this, the Woodford is this trough. And if you look at, I have my color bar, I keep my troughs in black and my peaks in orange. I call it my Halloween color bar. I've used it for 30 years. But this black trough right here is basically the Woodford section itself. And the Woodford ends up being the source rock for the Merrimack production. So basically, we're looking at this interval between the pink and this yellow, which is the base of the Woodford. That's my horizon limits. And one thing I want you to notice is that as you start on the north side of the survey and look at the south side, you can see an expanding section. So the Merrimack is getting thicker and the Woodford is getting thicker. So that should be one clue as to why my really good well down here might have produced a little bit more than the wells to the north, which were generally poor wells. Now, one of the things I go into is I look at principal component analysis. I generate about 17 or 18 attributes, all instantaneous attributes at first. And in this case, I did not have any AVO data. I didn't have any angle stacks or offset stacks. I only had PSTM volumes, and then they gave me a series of inversion volumes. I probably won't talk much about the inversion because they didn't work well. But my opinion about inversion is that it's good where you've got a lot of well control, but it's a modeling process in and of itself. So when you get very far away from your well control, the model starts to fall apart, as opposed to classification or SOM, which is one neuron equals the same rock properties wherever you see it in the data. But I went through principal component analysis and looked at all 16 of my instantaneous attributes. And in the first eigenvector, it started breaking out those attributes which were more pertinent to successful classification in the volume than some of the other attributes. So right off the bat, I see 5 attributes that contain about 70% of the data that all 16 would have. And in looking at the eigenvalue numbers, you can see a lot of variance in the data set. The way Paradise works is it does this principal component analysis on every inline in the data set. And the green line represents the median for the whole data set. But you can pick any one inline and look at the values and the appropriate attributes that show up in the top of the eigenvector anywhere you want, or do a group of across a field. So I used a recipe looking at first the top attributes in the first 2 eigenvectors. So in this case, I've got attenuation, envelope, Hilbert, instantaneous frequency, instantaneous phase, normalized amplitude, relative acoustic impedance, sweetness, and thin bed. And what I noticed right off the bat is here's my really good well. This is the 240,000 barrel well right here. Is unlike a lot of the other wells in the area where they had just perforated the whole Merrimack section or the majority of the Merrimack section, the operator on this well perforated a bulk of it and then did spot perforations in 2 other areas. And I got to looking at the area down here that had unique neurons or classification clusters that were not apparent at the base of any other well or very many wells in this section. And so here's neuron number 71, which is kind of brownish in color. and neuron number 72, which is yellow. And you can see the yellow and the brown over here occur just mainly around the efficacity well and a couple of other areas, but not very consistent in the rest of the section. So what I'm able to do is I am able to go in and kind of squeeze down and look at these. And when I pulled up the appropriate log curves for the efficacity well, I noticed that the two sets of perforations right here and right here corresponded to better resistivities in that well. And of course, sometimes the better resistivities in an unconventional play indicate rock that's more brittle and can be fracked more easily, or it might contain a sandier section with the hydrocarbons, a higher TOC. So I was especially interested in this lower zone, again, where I had neurons number 71 and 72, and it had the highest resistivity of anything else in the well in the Merrimack section. So I can isolate those two neurons. I can turn everything else off and isolate just those two neurons and where they occur in this whole 195 square mile area. And we can do that because we can take the upper horizon and the lower horizon and we can squeeze it down to eliminate spurious information and just concentrate on our zone of interest down here, which are these two lower sections of perforations, what I call the sculpted interval. And when you do look at that, you will start noticing that the efficacity is right here. This area were my medium wells, and everything else, if we go back to the production map, everything else was in the poor category. So that tells me right off the bat that these two neurons are probably key to not only porosity and permeability, but also to production in this whole area for the Merrimack. Now, one thing we can do is we can take the voxels, because we know that there is a sample height, in this case 1 millisecond, and the area, the bin spacing of the 3D, and we can turn those voxels into actual little volumes. And this is a process we go through to create geobodies. And once you have your geobodies created, then if you know very specific information, you can turn around and turn those geobodies into and look at them in terms of reserves. So that's what I did in this process. This is the geobody that corresponds to that lower zone of perforations. And the assumption I'm making here is that is where the predominant amount of hydrocarbons came from, because it's the highest resistivity. It was a very specific zone that they perforated, and it's abundant around the efficacity well. So if you know, I have the sample counts, interior and exterior. If you know the velocity of the rock, you know the net to gross ratio of your zone of interest in that geobody, you know your porosity, and you have your water saturation, then you can calculate how many hydrocarbon pore volume in cubic feet, now we can do this in acre feet as well, would be attached to that particular geobody. So what I did is I have a buddy who worked for a larger independent who was in charge of the Merrimack group in Oklahoma. And I just asked him, I said, what are your engineers using for numbers in this area for their reserve estimates? And he came back with 14,000 feet per second for velocity. He said, generally they're using a net to gross ratio of 60%. We're looking at 6% porosity, you know, for some of the better wells, and we're looking at a 40% water saturation. So when you take all those numbers, and he also told me that they're getting roughly about 250 barrels of oil per acre foot, then I can go in and I can look at that number and compare it to the actual produced number in the well. So I did that, divided by 43,560, and I got 2,725 acre feet for this green geobody. And I multiplied it by the 225. I said 250 earlier, but it's 225 BOE per acre foot. And I came up with a number of 613,125 BOE. So what I did is I took the oil production and the gas production in the efficacity, and I converted the gas to a barrel of oil equivalent. And what the well has actually produced is 611,685, as opposed to the calculated amount. Now, this well is still producing. It hasn't been plugged. It was drilled in 1980. So it's been producing 50 years, which is a long time, or to 40 years, 41 years, and still has some production left in it. Of course, you never get everything out of the rock, but if you look at the number of actual compared to what I calculated, I'm only basically 1% off in error. So that's pretty good. I would challenge most engineers to get that close when it comes to estimating reserves. And so I came back and had a meeting with TGS and showed them my results. And they said, well, I mean, you could have gotten lucky by estimating the reserves for the efficacity. What about the group up here that were the medium group? And it turns out here's the 3 or 4 wells that are actually in the medium range. They're cumulative in barrels of oil equivalent values. So the cumulative total for those wells is 581,883 barrels of oil equivalent. So I went back in and I looked at them, and 3 of the 4 wells actually penetrated the 71 neuron, but this last well over here didn't perforate in that neuron. It perforated in a zone up here just above the Merrimack. And if you look at the blow up of the neural information, you can see that the number 72, the brown neuron right here, they perforated in there, but this well did not. So and they didn't have any of this. They didn't have any of the yellow number 71 in here like the efficacity did, which probably gave it so much better production. In looking at them, here's the 72 neuron here in this well and here in this well. And this well had it, but it didn't perforate in it. What's interesting is the zone of perforations in the one well and the three zones above the Merrimack also perforated in 71 and 72. So the 71 and 72 neurons are indicators of better resistivity and hydrocarbons. Totally unrelated to what we're seeing down here in a different complete section, but the same neural information. So I went back and I looked at the geobody associated with that neuron. And this well right here did not produce from that neuron in the zone of interest, but this well right here, the McClinda or the Cyclinda did. So I took out the production from this well, I took the production from these 3 wells and this well, and ended up with 481,681 BOE equivalent, as opposed to the 475 that they'd actually done. And then added the Cyclinda to it. And so the bottom line here is the 4 wells which did produce from that geobody was less than a 2% error to what the actual production was and what was calculated. So again, it looks a little dendritic, but if you're looking for a sandy zone in an unconventional reservoir, or you're looking for porosity streaks, you would expect it to look something like this and not just a big clean reservoir. So after that, TGS was happy with the work, and I think that they actually have Paradise up in the cloud along with their data. So if you're a data subscriber to TGS data, you have access to be able to use Paradise to do your work with their seismic data. And a follow up on that, Paradise has the ASPE consortia software in it. And that's Kurt Marfort's group out of the University of Oklahoma. We licensed that software to run geometric volumes in. And so this is an example of a time slice roughly at the base of the Woodford, showing little channels and stuff in the Woodford shale itself that are coming through in the similarity volume. And I can also look at fractures. This is 17 milliseconds above the base of Woodford, roughly about the zone of the lower perforations in the efficacity well. So I can definitely see some fracture trends. Now I think there's some busts in processing right in here that TGS was not aware of. But this software is pattern recognition. So if there's a pattern in the data, it's going to pick up on it. And yet the unintended consequences sometimes are picking up acquisition footprint, bad seams and merges, processing busts. There's all sorts of patterns out there, coherent and incoherent patterns that you can pick up with neurons other than just geology. But there's some definite fracture trends in here that you can see going on throughout the Merrimack. And I ran a SOM using 2 curvature volumes and 2 similarity volumes so that I could turn on and turn off clusters. And it turns out that the vast majority of fractures and liniments in here can be seen just with 4 neurons. So I thought that was pretty interesting. So the conclusions from the study is that SOM can be very effective in finding sweet spots, even in unconventional reservoirs. Now, I find them all the time in conventional reservoirs, and we're getting ready to get into that, especially where there's changes in deposition, siltstones, calcareous sands, etc. And I've even used this process in West Texas in the Bone Springs and the Woodbine, not the Woodbine, Wolf Camp, to find little thin calcareous sand channels and stuff, even in those environments. Geobodies can and are related to finding porosity streaks and can be back calculated to production for use in reserve estimates. And it's very accurate. It's a good way of going forward to estimate new sweet spots which have not been drilled. But the key to all this is understanding the depositional environments. I mean, applying the geology to what you're seeing in the seismic data, tying to wells with synthetics, because here, unlike a wavelet where you kind of be loosey-goosey with your synthetic, you're tying to very specific neurons that are sample-based. So you need to know with good synthetics what you're tying to. And then also understanding the function of attributes that you're using in your analysis. Some of them are good for stratigraphy, some of them are good for porosity, some of them are good for hydrocarbon indicators. So it's the combination of attributes that you use in your, what I call recipe, that are going to get you further down the road in understanding what's going on in the subsurface. So next, I'm looking at exploring in a conventional play in East Texas. And the premise behind this study, which was more recent than the Merrimack study, is I had a client who operates a field and actually ends up owning a lot of the minerals in a very good East Texas field, which was discovered back in the 90s. And there's been a lot of good wells, a lot of production out of this field. This is another proof of concept for them to see if unsupervised classification on a sample scale could help identify a reservoir rock in Cretaceous sands below 13,500 feet. So in the Merrimack world, we were dealing with rocks around the 8,500 to 9,000 foot range. And now we're getting deep. We're in the 13.5 to actually 14.3 range across this 3D. And to see if there were any remaining locations left to be drilled. They thought they had gotten it all, but there was always hope that there was 1 or 2 spots that they left behind. And again, they gave me a 3D survey, a PSTM only. I did not have gathers. I did not have any outstanding AVO volumes or angle stacks. They gave me wells, production tops, and a lot of digital logs. So this first map you're going to see is a map on the key horizon just above the productive Cretaceous sand. And this map is based on the unconformable surface below, and I can tell you it's below the Austin Chalk. The base of the Austin Chalk is an unconformable surface, and this Cretaceous sand is coming up and butting against the unconformity. I have 2 cross sections I've built in here again, a west to east cross section and a south to north cross section. Now in this case, the wells with red squares around them are those wells in which I've created synthetics. And there is a very good velocity variance across this 3D as you go from south to north. where the section is thickening again and you're getting deeper, and from west to east even. And there's a big fault over here that you can cross over, and there's a big velocity change across that fault. I've turned off all the shallow production because there is shallow production in here. So everything that's shown is 12,000 feet deep or greater. Now, the south to north arbitrary line is what you're looking at right here. And this is the unconformable surface that we're going through in this area. And the sands, it's probably a little bit harder to see here, but generally what is happening is these Cretaceous sands are coming up unconformably and hitting the horizon, and they keep coming up, and so sometimes across the area you may see 5 or 6 different sands, and they're not the same. They have different rock qualities, but the production in here is, you know, from very poor production to some medium good production. This is a 24 BCF well that made over almost 1.3 million barrels of oil. So and you can see the perforations in here. Now, the west to east, the sand is a little bit harder to map. It's a little bit more spurious in its occurrence, but the premise is still that this is an angular unconformity and they're coming up in different zones and butting up against it. This actually goes through my very best well in here, which made 33 BCF and almost 1.8 million barrels of oil. So there's a 26 BCF well, and then you get over here to some poor wells that are even structurally up dip from good wells, which you'll see the difference in the rock quality when we get into the SOM. Now, I did the same process here. I took all of my instantaneous attributes that I created from the PSTN volume, and I went in to look at principal component analysis. And so right off the bat, the top 5 in the first eigenvector happen to be relative acoustic impedance, which to me is a porosity indicator. Envelope, Hilbert, envelope second derivative, and then sweetness, which I use consistently in the Gulf Coast as a hydrocarbon indicator. So we're getting the top 5 group right here, which is again over 60% of the relevant information from all the rest of the attributes used in the analysis. This is the south to north after processing, and here's my recipe. So I'm using thin bed because some of these sands are very thin sands. Relative acoustic impedance, envelope, attenuation. I threw attenuation in there because there's a lot of gas associated with this, and I wanted to see the effects of the gas in the SOM. So right off the bat, I've started looking at the perforations and identifying those neurons which are repeated over and over again in some of the better wells. And here you can see a combination of number 37, 47, 48. Now, these are just clusters. I haven't ascribed any rock properties specifically to them. I'm just looking at the way that they accumulate or assimilate next to the production in the wells. And I have the production for each well in here. So, and number 37, which is this darker blue, and number 47, 48, which are these kind of teal colored neurons right here. Again, 37, 38, which are blue. So there are some neurons that in the better wells, 12 BCF, 8 BCF, you don't see them so much in the 1 BCF, but again in the 7, that keep showing up over and over again. And then when I look at my west to east, here again, I've got some wells that are poor, that are structurally higher than some wells that are very good. Now, for the first time, you start seeing this yellow neuron come in. And here is the very best well in the field, the 33 BCF well again. This well, after talking to the operator, because I was concerned that I have all this yellow, and he said they had a 300-foot thick sand. It was the most beautiful sand they've ever seen. Permeability and porosity and gorgeous. It was just down thrown across the fault with a water level in it. So the fact that this yellow neuron is associated with the best well and one of the poorer wells has only to do with structure. It has nothing to do with the quality of the neuron itself, which I believe in here without having angle stacks is not showing me fluid level as much as it's showing rock quality level. Now, what I've done, and this is something that's fairly recent in Paradise, is to be able to build cross sections and actually extract SOM information or neural information along the cross section. So now we can start, and again, this is it's valid only if you have really good synthetics and you know what you're tied into. So now in the south to north, I have started, I have kind of a grading system for the wells, poor being 0 to 5 BCF, fair being 5 to 10, good being 10 to 20, great, and then excellent is anything greater than 25 BCF. And I can start associating very specific neurons with wells in their category. 55 and 37 with a well that made 24 BCF. 6, 17, 18, and 27, and 20 and 48 with a well that was, you know, in the medium or good range. So I can start quantifying the neurons with the production in these wells. And I did that on the south to north cross section. And again, my zone of perforation is right here, and in my west east. And again, here is my really good well, and the well that was down thrown. I don't have a log on that well, down thrown. And when he's saying that it's a really thick sand, I'm assuming that that 73 is covering that sand, but only perforated in here because they hit the water level. So I can start to get a feel real quickly which neurons are good, which ones are medium, and which ones are associated with poor production. And what I've done here is I have, much like in the Merrimack, is I've pulled up all the neurons within that zone of interest. And I think I went from the unconformity down 30 or 40 milliseconds because the bulk of the production is within 30 or 40 milliseconds of the unconformity surface itself. And what you start to see with the poor, the fair, the good, the great, and the excellent is you start to see some of the better neurons associated with the east side of the field and some of the poorer neurons with the west side of the field. And they break out, you know, interestingly enough, in clusters that are pretty much at polar opposites in the whole map. And so what happens is clusters that are close together have very similar properties, but just enough to distinguish themselves in separate clusters. So this group is very similar to each other, but in 4 separate clusters. So this is the group of poor neurons associated with poor production. And these are the neurons that are associated with the good to better production and excellent production. And I can look at each layer independently and then look at the associated attributes that go with that layer and their contribution to that cluster. So in this case, the yellow layer, which is with the best well, and here's my best well right here, and you can see the cross-section lines coming through, is Hilbert relative acoustic impedance, which again, I'm using as porosity indicator, envelope and sweetness, which can be hydrocarbon indicators. And then everything else is not contributing that much. So here's neuron number 73. Here's neuron number 55, and again, the associated neuron independence that goes with the attributes there. And then finally, here's neuron number 37. And you see attenuation starting to come in along with relative acoustic impedance. So you're starting to see some of the gas effect coming in this neuron, and here's the best well. Now, similar to what I did with the Merrimack, is in Paradise, we have the ability to look at data based on the probability of those data points being in the center of the cluster. And so each cluster has a scattering of data points that make up that cluster. What I've discovered over the years is those data points which are on the peripheral edges of the cluster, yet still being part of that cluster, are the most anomalous to that cluster. In the Gulf Coast, if I have angle stacks or offset stacks, or I have gradient intercept, I have AVO volumes that I'm using in my analysis, I have found that the AVO effects are most concentrated in these outside clusters. Excuse me, one second, I'll get a drink. So what I want to do is I want to turn off all the data points of the clusters and only look at the outer 10% of information, which is my most anomalous information to this area. And when I do that, you see a lot of the data goes away. Now, this 3D was shot well after the field had been discovered and was being developed. So let me go back to, excuse me. Let me go back to, here's all my clusters with all the data points turned on. Now, when I only look at the most anomalous 10%, what I think I'm seeing here is I'm seeing signs of depletion in the field. There's nothing anomalous about these areas anymore because they're all depleted. However, there are 4 zones around the edges of the field which have not been depleted. Now, I killed this one because it has a dry hole in it, and if you peel off the layers, it has a lot of the bad neurons in it. But this little area right here, this well right here, deviated well, is the base of the well is right here, so that production sign is not pertinent to this zone. And 2 zones that are down here that have substantial size to them, and you can see the green and the yellow and the blue that's associated with what we saw in the best well. Now, this area right here is downthrown or lower, so it may carry a little bit higher risk with it. But for right now, these are my 4 zones that I'm seeing that are left after depletion. And so I created geobodies with them. And so I want to go in and look at the geobody information now. But before I do that, I want to prove to myself that what I think is a good neuron for production in here is actually so. So here's one of them I'm looking at, and just off the cuff, if you look at the areal extent of the geobody and the neurons in it, you're coming up with numbers that if you were assuming a velocity of 14,000 feet per second and a net to gross ratio of 80% in here and a 25% water saturation and a 30% porosity, then you can come up with this area right here, which is dry holes on one side and an old producing well on the other, but not depleted. Then you can put 20 BCF and 1.1 million barrels of oil in that blob. Here I've taken 15% of the yellow because I can't run a geobody on low probability information, but I'm still coming up with 13.5 BCF and 727,000 barrels of oil. And the 2 areas to the north are a little bit smaller. They're in the good category, 8.6 BCF and 460,000 barrels of oil. And finally, 5.5 and 298,000 barrels of oil. Now, that's my estimate based on the fact that I think that these geobodies are related to neurons, which are related to reservoir quality. And these are $6.2 million wells, so they're not for the faint of heart to drill for my client. But he said, okay, that's good and well, but how do you prove that those are good hydrocarbon neurons? So one of the ways we have of going about looking at it is to look at bivariate statistics. And this is, we're going to go back to the cross sections now and the neurons that were associated with the wells. So I can put wells in and I can tell it the zone of interest I want it to use in this, and I can pull up the associated SOM classification volume that I ran, and then I can give it some very specific petrophysical cutoff information. In this case, I'm looking for gamma values less than 660. I'm looking at 10% porosity or greater. I'm looking at a water saturation. I'm looking at 6 ohms or greater of resistivity when it comes to what determines what's wet and what's not. And then in the chi-square table, I can actually, if I had multiple runs with multiple topologies, this happened to be an 8x8, then I could go in and it would tell me which topology it thought was the best for the analysis. But what happens is, when you give it the cutoffs and you give it the zone of interest to look at, it's going to look at all the neurons in that zone of interest. And it's going to determine which ones are really related to reservoir quality or reservoir and which ones are not. So in this example, this good well right here, which produced 26 or 12.6 BCF and 175,000 barrels of oil, it's looking at neuron number 38 and neuron number 41, which happen to be the two neurons associated with the production, and said, yes, those are reservoir rocks. Now, neuron 63, which is, up in here, has some reservoir in it, but it's mainly non-reservoir. And then the chi-square will do a null hypothesis theory and will tell me it's rejected or accepted. In this case, the null hypothesis is rejected, which means that the alternate hypothesis is that there is a relationship between net reservoir and lithological contrast SOM variables. For most people, in the past few years, they have looked at the SOM work that we've been doing or I've been doing, and to them it's a black box because they keep trying to go back to rock properties. Well, here is where you can take the black box out of it and associate specific clusters of information with reservoir quality rock. So that's a case for the good well. Here is a poor well, which only made 165 million cubic feet of gas and 2,800 barrels of oil. Well, I looked at the perforations across that reservoir, used the same basic cutoffs, and here I'm looking for greater than 8 ohms of resistivity and 8% porosity. And it's telling me that it's got some reservoir in those two neurons, but it's telling me most of it is not reservoir. And based on the poor production and the really tight sands or ratty, shaly sands in here, I can see why I don't have a lot of good reservoir and why the well produced poorly. Now, it's still saying that there is a relationship between the net reservoir and lithological SOM contrast, but it's just telling me I have more non-reservoir than I have reservoir. And that, again, it's held up by the poor production of the well. Now, for the final well that I looked at was my best well in number 73, 35, and 55. And here, it's telling me 55 and 73 are definitely reservoirs, but there's a little bit of non-reservoir 73. And if you look over here at the perforations, you see this area that's a little bit wetter and a little bit shalier. So it's picking up on just that piece of reservoir, which is non-reservoir, and letting me know that there's some non-reservoir in there. And again, it's rejected the null hypothesis and telling me that there is a relationship between net reservoir and lithological contrast SOM variables. So here's a way I've been able to go in and evaluate a field and look for pieces that were left over and verify that the geobodies left in these areas can contain, if one wants to go in there and drill it, an amount, all 4 areas is equal to somewhere over 55 BCF and close to 4 million barrels of reserves left in this area. You just have to want to gut up and spend $24 million coming in here and drilling these areas. So the summary and conclusion on this is that I can go in here using multiple seismic attributes and show patterns in the earth that you can relate to reservoirs when calibrating to wells. That the use of geobodies, again, can predict accurate volumes of potential hydrocarbons when you have the correct input data. And that here, the use of low probability can help identify stranded reserves in a field. And I've done this in other fields. I just don't have the show rights to be able to show you guys. And the application of statistical petrophysical methods can verify and reduce risk in identifying reservoir grade rock in the potential stranded areas. Now, this workflow is not one and done. I don't stop at one recipe. I'm constantly playing with it and looking at different topologies, the number of clusters I'm using to identify. But it is a very good statistical methodology to go in and look for stranded reserves. So that kind of is the end of the unconventional and the conventional case. The last thing I want to show is some of our latest work that we're doing in the work of the SOM work, and that has to do, and I want to thank TGS and my Texas client, and a big thank you to Carrie Lawden of Geophysical Insights for guiding me through the statistical analysis process, because when I did this last year, on this East Texas field, I was clueless as to how the bivariate statistics process worked. This last stuff is some stuff I've been doing in northern Colombia. And we're getting into convolutional neural networks now and associated with SOM, and working with the ASPE software that we have in Paradise to look at how we can go through and eliminate the need for manual picking of faults, which is the most dreaded thing a geoscientist has to do when they get a big survey. This survey happens to be about 400 square kilometers in northwestern Colombia. And you can see it's very complicated when it comes to the fault regime. Now, what we've done is we've taken a 2 millisecond sample volume, and we have created a neural network of basically faults in here. But we've upsampled it to 4 milliseconds to run it through our convolutional neural network. This gets rid of unwanted noise and possible false positives. Then we can go into the ASPE software and take the CNN fault volume and skeletonize it down to just the basics, getting rid of false positives, again, noise, and getting it down to what looks like a valid fault interpretation volume in this area. So I bring this into Paradise as an attribute volume, and I can pull it up in the 3D viewer and look at what I believe would be the fault planes as opposed to the fault background in some of these other areas, the white areas. And then I want to use it in SOM in classification. So I will use it in combination with instantaneous attributes and get something that looks like this. So now I can see my fault planes, and the faults clearly associate themselves in one corner of the 2D map that we have in the 3D viewer. And I can go in and then turn on the instantaneous attributes that I believe are associated with the reservoir rock. And I'm going to focus on this one well right here, because this is a well that was recently drilled by the client and came on pretty well for gas, but then watered out. So they're wanting to understand an explanation of why it might have watered out. And I can see stratigraphy along with the fault web itself. So here's a close-up of that well, and it's very close to the fault. And what I think happened is I can see the different layers of the perforations. They perforated 3 different zones in here. And it was the upper zone that watered out at the very, very end. And not only do I think that they probably coned water up through the fault plane, but I think that the upper reservoir, which finally depleted, either depleted on test, or it was compartmentalized to where it wasn't very big in association with the water they were getting up the fault. Now here's the reservoir neurons and the fault neurons. And here's another look at it. So they can come up dip and get past this compartmentalization right here. But then the question is, does this fault go all the way through? And this is an upper structure right here. So maybe the gas has migrated. You got some low saturation gas in here, which could be contributing to the watering out. And maybe the good gas is all migrated up around this fault into this upper structure right here. So here's my reservoir neurons, here's my fault neurons. If I had this in the 3D viewer right now, I could rotate this around and you would be able to see how beautiful these fault planes are coming out with that skeletonized volume in SOM. And so with that, guys, I say that's the end of my presentation. If Susan's ready to take questions and send questions my way, I'll do my best to be able to answer them.
Great, thank you. So why don't we take a look at some of the questions? Let's see, I've been taking,
And I'm going to get out of this, Susan, real quick so that I can go back to any one slide. If people kept a notice on the numbers of slides, if they have a question to a particular number of slides.
Okay, great. And I don't know about a PDF of the slide presentation being available, but you will have the recording available. And here's a question. Is the vertical window of neurons completely random, or can you give it a certain minimum thickness?
No. In fact, a lot of times what I do is you can go above or below a horizon in milliseconds if you want, or depth. All this is generated in depth volumes as well as time volumes. But a lot of times what I will do is I'll do a window between two specific horizons. And basically the only interpretation I do in the conventional world anymore is major flooding surfaces, because I use those as my horizon delimiters. But no, you can do it by time, you can do it by horizon, you can do it just about any way you want.
Great. Here's a question from James Hill. Will this technique work on 100% 2D data?
Absolutely. Now, getting into some of the geometric volumes, you know that the geometric volumes are multi-trace calculations. So generating a similarity or coherency volume or curvature volume is always a little bit iffy when you have 2D data, because you're looking at one line of trace instead of multi-traces. That's not to say that you can't do it, but certainly the instantaneous volumes. I've got a prospect in South Texas right now that I only have 5 2D lines on. So we're hoping to get enough interest to shoot a 3D in there before we drill a well.
Another question from Kimberly Wagner. What kind of well density is needed in order to get reasonable or reliable results with this sort of analysis?
Well, you can do this without wells. I have done offshore West Africa for a client without any well control at all. You run a little bit higher risk in doing that, but if you can start seeing flat spots, if you can see distributary sand systems, you see patterns that are geological in nature. You don't have to have well control at all. You have to have a good concept in geology and understanding the attributes that you're using to be able to pull out information. You definitely can see flat spots if you're using fluid type attributes, AVO volumes.
Great. So Valentina Bodanova is asking, are SOM and PCA considered deep learning?
In my mind, they're deep learning. They've been around for a long time. People might think that the convolutional neural networks are probably deeper learning than SOM, but I've been using this process for about 10 years now. I probably worked on between 150 and 200 different surveys around the world. And the classification process for understanding the subsurface stratigraphy and what Mother Nature has given us to work with is so superior to anything else you can do in the conventional seismic world. I can't ever go back to conventional wavelet data again. Every time I look at wavelet data, my mind is trying to imagine the subtleties of the clusters that are going on in the background.
That's interesting. Patrick Ng comments that think of them as tools in a toolbox. PCA is one of the tools in data science. SOM is one of the earlier developments in clustering algorithms. So don't know if you have a thought about that. Okay, has anyone used this type of analysis for geosteering horizontal wells? This is from David Brumbaugh.
So David, we have several clients that are in the unconventional world, and I can tell you that based on the detail they can see, especially like in Eagleford, when we can zone in on the sweet spot in Eagleford, they definitely are using it in geosteering.
Interesting. So Bob Frickland asks, is Kingdom the best software for doing all of this?
Well, now Kingdom is not part of Paradise. I happen to use Kingdom. I'm an independent, Kingdom is a lot cheaper than Petrel for me out here in the country. But the only thing I do in Kingdom is I bring the volumes in, I upsample them, because what we found that you can resample the data one time, like going from 4 milliseconds to 2 or 2 milliseconds to 1, and not introduce a lot of artifacts, but you get better statistical information and better resolution. So I use Kingdom for some functionality, but all this work is done in a completely separate program that we call Paradise.
Thank you. That was a good differentiation. So James Hill comments, it seems that your estimated production in the unconventional Cassidy well suggests that the majority of the reserves has been produced. Would you recommend a refrac in this well?
Well, I mean, what you're not seeing on that map is all the horizontal wells that have been drilled in the Merrimack since that well was drilled in 1980. So we're looking at a well that probably has a very little life left in it, and any life that's left in it is probably being consumed by those wells around it, which were lateral wells not shown on the map.
Interesting. That's good to know. Trevor Richards, and this is probably our last one, asks, have you seen any effects that you might link to production effects? It seems that this could be a powerful tool for characterizing stimulation areas and production effects in mature field areas.
Absolutely. I mean, again, just because of the accuracy in the geobodies that I've been able to work with, I would probably put this up against any reservoir simulation model, not only from the detail that you can see in SOM at 1 millisecond resolution, but from the accuracy when you have the known amounts of porosity and permeability and velocity and stuff that you can get. So not that I want to become an engineer in my later life. It's bad enough to go from a geologist to a geophysicist, but I can take this tool and I can go full circle for my clients with some reliability.
Well, that's great. So we've come to the end of the hour, and I'd like to thank you, Deborah, and also like to thank our sponsor, Geophysical Insights, and really happy that they've sponsored this Lunch and Learn and appreciate their generosity. And also would just like to remind everyone that you will be getting an email with a link to the recording. And also would like to ask you if you are interested in any other Lunch and Learn topics. I'd like to say thank you to Patrick Ng and let him have the chance to say a few last words.
Certainly, Susan and Deborah, really enjoy your neurons presentation. But one comment is that what you're showing us is perhaps, like many over decades, we've seen geologists, they're very good looking at things that we don't see. But that's biological neurons. So what you're showing us today is the use of these artificial neurons, and combining the two, you think will be better, beating the odds of getting these successful, maybe we develop these assets and looking for new ones. Yeah, well, Patrick, one last thing I'd like to say is a lot of people think that machine learning is going to get rid of interpreters. I say we're going to need more interpreters because and interpreters with experience, because you still have to interpret the results of this and combine it with well information and understanding of geology to make sure that you're on the right track and that you're accurate. So machine learning can make life easier in terms of fault picking, but we're still going to be needed to understand everything that it's doing. Thank you, Deborah. Thank you, Susan.
Thank you. Well, thank you, everyone. And thank you again to Deborah and Patrick. And we will see you in the next one.
Excellent. Thank you.
Bye-bye.